So, welcome to the uh, problem solving session for the week 8 contents of the course Geotechnical Engineering 1 offered by Professor D.N. Singh from IIT Bombay. So, I am Yogendra Narayana. I am a PMRF research scholar who has been conducting these sessions. So, these sessions are uh, dedicated to make the learners proficient in the concepts of, of the course. Concepts of the course by solving problems from previous NPTEL assignments, question papers, etc., so that the learners can be proficient in understanding understanding the concepts and and be clear in approaching the problems in NPTEL exams as well as in future competitive exams as well as in their professional careers. So, with this, I would like to give a brief uh, recap of what the content has been covered in the previous uh, week, that is week 8. So, it was essentially on seepage theory and uh, flow nets, especially the emphasis was given on flow nets and how to calculate the discharge from a two-dimensional flow through soil mass by using flow net. It is just an extension of one-dimensional flow and Darcy's law to to extended to the second dimension. So regarding this, we'll be solving some problems. But prior to this, there are two problems that has been uh, left unsolved from the previous week. So start. I would like to start the session by solving those two problems and then proceeding to the seepage, that is the contents of week 8. So now let us move to the problems. So the sand layer of cross-section area as shown, the figure below, has been determined to exist for a length of 800 meters of the levee. So levee is nothing but the embankment that is constructed in order to retain the water that is of relatively lesser heights, unlike dams or reservoirs. So the hydraulic conductivity of the sand layer is 2.8 meter per day. Determine the quantity of water which flows into the ditch. If the sand has a specific gravity of 2.65 and the layer is made up of dry density of 16 kilonewton per meter cube, calculate the seepage velocity. So right now the figure is given. Now we have to approach the problem. So first let us list down what has been given. So length in the third dimension, that is this direction. Length goes up to 800 meters. That is L. Let us take as ideally it should be taken as L. So length of leaving 800 meters and the thickness of sand layer 1.6 meters. 100. Now, now hydraulic conductivity is given. K will be 2.8 meter per day. So, and the property of the sand layer is given, for which GS is 2.65, gamma D is 16 kilonewton per meter cube. We need to find out seepage velocity Vs. So how Vs is defined? Vs is defined as discharge velocity by porosity, right? So we need porosity. Porosity is defined as E by 1 plus E, and V is Ki into A. So we know the hydraulic conductivity, which is K. Now we need to calculate the cross-sectional area through which the flow is occurring and the hydraulic gradient across the flow path. So the flow path is of length, flow length is 180 meters, and the head loss delta H is 160 minus 145 meters, because head loss is nothing but the head difference between the upstream and downstream winds. So the total head loss is 160 minus 145, which gives us 15 meters of head loss, and flow length is 180 meters. So I will be 15 by 180. So which will give us 1 by 12. This will be 1 by 12. Now coming to the cross-sectional area. Area is, let us assume a rectangular cross-section. So that is the length of the levee into the thickness. So that will be 1.6 into 800. Now let us substitute it. It will come 2.8 meters per day into I will be 1 by 12 into area is in meter square, 1.6 into 800. Now this can be written as, now if you calculate it, you will get the 2.8 into 1.6 into 800 divided by 12. This is not the velocity, this is Q. And we first the quantity which we have to determine is to determine the quantity of water that flows into the ditch. So that will be, how much it will be, 298 meter cube, and the velocity of flow will be, discharge velocity will be V is equal to Ki, which is 2.8 by 12. So which gives us 2.8 divided by 12. So just a minute, I will write like this. So V is 2.8 by 12, which gives us 0.233 meters per day. So this is the discharge velocity and this is the discharge. Now we have to calculate the porosity. So for which we know the formula. So these details are given. So I will erase it. Just for sake of space, just erase it. Now coming to dry density, which is defined as gamma W Gs by N plus E. So we need the gamma W. Gamma W can be taken as 10. Gamma D is 16 is equal to 10 into 2.65 by 1 plus E. So if you calculate it, 10 into 2.65 divided by 16. So E will be 0.66. Now porosity will be N is equal to, substitute in the formula, E by 1 plus E, 0.66 divided by 1.66. So which comes around 2.4. Now Vs will be calculated as 0.233 by 0.4, which gives us 0.233 divided by 0.4, which gives us 0.583 meter per day. So the seepage velocity. So ideally, all the three unknowns have been calculated. First is the discharge that takes place through the sand layer. That is the discharge through the sand layer and which gets collected in the ditch in the downstream end. That comes to around 298 meter cube, and the flow velocity is, that is the discharge velocity is 0.233 meter per day, which is from Darcy's law, and seepage velocity comes to 0.583, which is obviously reasonable because it is greater than the discharge velocity. So by we know that the seepage velocity will be always higher than the discharge velocity. So by that logic, whatever the value we get is this, which is higher than 0.233. So these three are the uh, values which are demanded by the question. Right? Now coming to the next question. So So coming to the next question. Is my slide visible and am I audible clearly? Fine. So a permeability test on a clay sample yielded the following values. A permeability test on a clay sample yielded the following values, which is uh, the Voigt's ratio is 1.1 and the hydraulic conductivity is 0.302 into 10 power minus 7 centimeter per second. And for another compaction conditions, Voigt's ratio of 0.9 and hydraulic conductivity of 0.12 into 10 power minus 7 centimeter per second. Estimate the hydraulic conductivity of the clay if the Voigt's ratio is 0.75 when K follows the following relationships. So now the relationship between the hydraulic conductivity and void ratio is given. So what is the relation? That is K is some constant into e power some exponent by 1 plus e. Right. So we now need the hydraulic conductivity for E is equal to 0.75. Right. So for that we need C and N. Right. Now how to determine this C and N, which is a constant? So for that we have two conditions for which the both the Voigt's ratio and hydraulic conductivity is given. So if we solve these two equations, then you can get the value of C and N, and then you can substitute the value of 0.75 in this equation, and you can get the value of the permeability, coefficient of permeability. So now K is 0.302 into 10 power minus 7 is equal to C into 1.1 n by 1 plus e, which comes to 2.1. Right. So this can be rewritten as, you take this to this side. So you take this to here. Zero 0.302 into 2.1, which gives us 0.634 into 10 power minus 7 by 1.1 n is equal to C. So this will be equation 1. So the second equation will be 0.12 into 10 power minus 7 is equal to C into 0.9 n by 1.9. Now take this to this side. 0.12 into 1.9. It will come to 0.228 into 10 power minus 7 by 0.9 power n is equal to C. So this will come to equation 2. right? So equation 1 and 2 can be equated since the right hand side of the equations are same. So when we apply this 0.634 into 10 power minus 7 divided by 1.1 power n is equal to 0.228 into 10 power minus 7 divided by 0.9 into n. Alright, so this and this will get cancelled. You can bring the n to one side. So this will be 0.634 by 0.228 equal to 1.1 by 0.9 whole power n. Right? So you can divide this now. 0.634 divided by 0.228, which comes to around 2.78 is equal to 1.1 divided by 0.9 will come to 1.22 power n. Right? So now you can apply log on both sides. So log 2.78 is equal to n log 1.22. So that can be. So those who have joined late recently, so you can just observe this question and and you can engage from the next question onwards. So this question is under the verge of completion, so that you can join from the next question onwards, or you can read the question and try to understand what has been done in meanwhile. So coming back to the question, so and please try to join at the right time. So already we are since there is a delay in joining, so uh, we are forced to wait for another 5 to 10 minutes after it re after 5 in order to start the session. And so this discontinuity will not be useful for you also. So all right, now coming back to the question. So applying log on both sides. So log 2.78 equal to n into log of 1.22. So you can solve this logarithmic expression. Log 2.78 divided by log 1.22. So C comes to around, sorry, n comes to around 5.14. Alright. Now substitute this n in any of this equation. I'm considering this equation. So that will give us 0.228 into 10 power minus 7 divided by 0.9 into 5.14 equals 0.9 power 5.14 gives us this value corresponds to 0.582. 0.228 divided by 0.582 amounts to 0.392 into 10 power minus 7 centimeter per second. So this is the value of C. Now substitute this value of C and N in this expression for the value of Voigt's ratio of 0.75. Now K is equal to 0.392 into 10 power minus 7 into 0.75 power 5.14 divided by 1.75. 0.392 0.75 over 5.14 divided by 1.75 into 0.392 to give us a value of 0.051 into 10 power minus 7 centimeter per second. So this is the value for the coefficient of permeability or hydraulic conductivity for the same clay when it is compacted to a Voigt's ratio of 0.75. So any doubts? Any doubts? Okay. Now let us move to the next question. So now we are entering the flow net, two-dimensional flow. So the flow net can be utilized for determining option A seepage pressure, option B exit gradient, option C seepage. That is seepage is this in the sense quantity of seepage discharge Q, and option D hydrostatic pressure. The flow net can be utilized for determining option A seepage pressure, option B exit gradient, option C seepage quantity, and D hydrostatic pressure. Any guesses? Any answers? Right. So coming back to the question, flow net can be utilized for determining seepage pressure, exit gradient, seepage and hydrostatic pressure. So coming to the first A, so seepage pressure is I into gamma W, that is seepage force into force divided by per unit volume, that is indirectly the seepage pressure which is getting induced. So for that you need delta H by L, which is I. So each delta H will depend upon the number of flow channels and number of equipotential drops. So function of number of flow channels and number of equipotential drops at each this one at each point. So that's why flow net will be useful for determining the seepage pressure. And coming to the exit gradient, so exit gradient I exit depends on delta H by the flow dimension the uh, of the exit flow channel or exit flow uh, grid. So that will be some that length of the this will be length of exit flow channel. So that's why this can be obtained only from flow nets. So we can use the flow net will be useful for calculating this exit gradient also. And seepage, obviously, since it is a two-dimensional flow, we know the relationship, which is obviously a function of number of flow channels and number of equipotential drops. So hence, this also automatically it's a no-brainer. It comes under the uh, one of the applications of flow net. And hydrostatic pressure, regarding that, hydrostatic pressure is nothing but the pressure head. And if we know the head loss that is taking place at each and every point, or you need at a particular point, you have to know the uh, hydrostatic pressure. So since it is pressure head, it can be obtained from total head minus elevation head. So for that, this can be flow net can be useful. So regarding this aspect, it can flow net will be useful, and especially on emphasizing the estimation of hydrostatic pressure or pressure head. There is a problem which will be solving either this week or if time permits, or in the next week initially. So that with that problem, you can understand how uh, pressure head varies during the flow during that is when the flow takes place uh, through the soil. All right. So hence all the four can be uh, estimated by using a flow net. So the right options are all the four. So it is a multi-select question. Any doubts? All right. Now coming to the next question. During seepage through a soil, direction of seepage is always option A parallel to equipotential line, perpendicular to streamlines, perpendicular to equipotential line, option D none of the above. Any guesses? It's a straightforward answer. So let us assume that this is a completely impervious dam and water is here. Um, let that downstream and this one. So now the flow takes place in this direction. So hence flow nets will be drawn. Let us assume uh, something like this. So, let this be the flow net. So this the horizontal lines are flow lines, right? Flow lines. And the space between two horizontal lines is flow channel. And the line uh, meeting perpendicularly, that is line intersecting the flow lines perpendicularly are equipotential lines, right? Now, so the flow occurs always parallel to the flow lines. So that means, and flow lines and equipotential lines are at 90 degrees, right? So hence, the direction of flow, that is direction of seepage, is the direction of flow of water through the soil mass. So now the direction of flow will always be perpendicular to the equipotential line. So this should never be forgotten. So the direction of flow will be parallel to the flow lines and always perpendicular to the equipotential lines. Right? Any doubts? So coming to the next question. Why sheet piles are provided and which is the preferred position for provision of this sheet pile? So first, the sheet pile is to decrease the uplift force and the exit gradient. Alright, so let us see how it decreases the uplift force or the exit gradient. So just a minute. Just a minute. So there is a. I'll just again. I will stop sharing and again I will share it. I hope the screen is visible now, right? So right now, what happens is uh, now we will see how it uh, decreases the uplift. What happens when sheet pile is provided. So now let us consider embankment, or this is let us consider this as impermeable and the flow occurs through it. So what happens as the flow progresses, the water exerts a pressure, which is the seepage pressure or uplift pressure. So the pressure exerted by water will be equal in all the directions. So the structure is going to get affected due to the uh, magnitude of force that is acting upwards. So hence it is known as uplift force. Now that depends on the amount of head that is present at each and every point along this surface, right? So along this line, along this direction, the uplift force depends on the head of the water that is present at that particular point. So in order to decrease the uplift force, you have to decrease the head. For that, you have how can you decrease the head? That is, you have to decrease the hydraulic gradient. So which is the head difference by the length. Now you cannot since the length of flow is say, that is the uh, the since now we have a water position upward and downward position. So this remains constant, and hence this delta H, total delta H is never going to change. So but the only thing which we can change is the length of flow. So what happens is that, so when we provide this sheet pile at the upstream end, so the water has to flow like this. And then the first flow line will be like this, right? Followed by others, or such a way that the length of the flow of water is extended. All right. This may not be this way, but this corresponds to the first flow line. So earlier, when the length was just this much, now if we are inserting a sheet pile of length LS, the total length of the travel of fluid will be equal to L plus 2 times L sheet pile, right? So this will get reflected here, and hence the hydraulic gradient will decrease, which will be reflected at each and every point. And hence, since the I is decreasing, uh, that is the not critical hydraulic gradient is decreasing even at uh, the exit point. The exit gradient will decrease, as well as the uplift force will decrease. Hence, the sheet piles will always be provided at the upstream end in order to decrease the uplift force and the exit gradient. Any doubts? Are you able to understand this? Or so the primary function of the sheet pile is to reduce the uplift force and the exit gradient. How it reduces is that it increases the flow path, length of the flow path. So that is how it's uh, the purpose is solved by using sheet pile. Hope it is clear, or you are finding it difficult to understand. Fine. Now coming to the next question. Where do filters are placed in a dam and why they are provided? So filters are placed due first aspect is to prevent the piping failure. So and uh, the major where they are provided is that, so now when we are considering an embankment through which water can flow. So if it is the upstream end and this is the downstream end, the water will can flow. This is the topmost flow line, which is phreatic line, right? So this will meet the water flowing through the embankment will come out of the downstream slope. So when it comes out of the downstream slope, it starts eroding the soil on the downstream slope, which will make the entire embankment unstable. So this is known as the this point of uh, exit of water from through the embankment uh, from the downstream slope is termed as outcrop point. And if the outcrop point is set is on the slope downstream slope, then the erosion will occur, which will in turn damage the entire embankment. So in order to that, always what happens is that the easiest way is to make this make the flow of water exposed to the atmosphere. So for that, what they do usually is they provide a filter at this exact toe of the dam, or this is rock toe filter, or the filters will be extended into the dam from the downstream end. So so that the entire from this part, this point across this filter length, the pressure will be atmospheric. So hence the flow line will come and meet here and not at the slope of the downstream end. So hence this entire piping failure can be prevented, and uh, the how to put it, the entire dam structure can be maintained in a stable condition. So hence the the filters are always provided at the downstream end and to prevent piping of the soil. So this is why filters are provided. The option C is right. Any doubts? Any doubts? So coming to the next question, the upstream slope of an earthen dam under steady seepage condition is, the upstream slope of an earthen dam under steady seepage condition is. So steady seepage condition is that the first we need to understand what is steady seepage condition. So this is an earthen dam. This is the downstream head. This is the upstream head, upstream water level, and this is the downstream water level. The head loss will be this much. So when the head loss is maintained constant, there is no change in head loss, that is delta H. So that condition is termed as steady seepage. That means there is no the entire flow, discharge and everything will be maintained constant since there is no change in head difference, right? Now what they are asking is that upstream slope of an earthen dam under steady seepage condition is. So this is the upstream slope, right? So this part is the upstream slope. Now we what we are going to do is we have to check whether the flow will act. There are two possibilities. So this slope can act either as a flow line or a equipotential line, right? So now for the flow to occur, there should be head loss. So let it be. Am I audible? Fine. So let this be the this is the upstream slope, and now this can either be a flow line or an equipotential line. So we have seen from the uh, earlier that is the problem which we solved from last week, that is between the water column there will be no flow of water. So hence this is not a flow line. Now how to determine whether it is a equipotential line? So now what we do is we place a piezometer at this point. This water is exposed to atmosphere, so it is under atmospheric pressure. So when you keep the piezometer, the water will rise up to this point. And when you keep a piezometer here, the water will rise up to this point. So when you keep the piezometer here, the water will rise up to this point. All right. So now, if you calculate the total head, that is the datum head, let this be the datum head and the pressure head. So the total head will remain same. So hence, at each and every point along the upstream side of this slope, the total head is remaining same, and hence it is a equipotential line. All right. Any doubts? So coming to the next question, to prevent the possibility of erosion and piping, the following approach, which of the following approaches could be used? That is, which of the following approaches could be used? Providing cut-off wall at downstream side, providing impervious blanket, providing protective filters. So providing cut-off wall at downstream side, that is cut-off wall is nothing but a sheet pipe. It is a sheet pile generally. Cut-off wall is nothing but the impervious wall to elongate the flow length. So that we have seen that it should be provided at the upstream side. So hence this is not the right option. So coming to the second point, providing impervious blanket. So impervious blanket is, it can be provided in two ways, whether it can be using compacted clays or by using, nowadays they are employing geomembranes in order to provide impervious blanket. So that is being carried out, and hence this option is right. And this is mostly done in the upstream side. And providing protective filters we have seen earlier, so that is to be in downstream side, and obviously they have not mentioned, so that is also an option. So option 2 and 3 is right. Hope it is clear now, right? Any doubts? Now coming to the next question. So equipotential lines and flow lines intersect each other at right angles. So obviously we have seen earlier several in 2 3 occasions that equipotential lines and flow lines intersect each other at each other orthogonally, right? So coming to the next question, what will happen if the hydraulic gradient is the existing hydraulic gradient is less than the critical hydraulic gradient of the porous media? So how to determine the safety or uh, criticality of this against piping failure or uh, quicksand condition, etc. So that we determine a term called factor of safety, which is defined as the ratio between critical hydraulic gradient to the existing given hydraulic gradient. So now if FOS is greater than 1, then safe. If FOS is less than 1, unsafe. And FOS is equal to 1, it is critical. Alright. Now for FOS greater than 1, IC should be greater than I. For FOS less than 1, IC should be less than I. And for FOS equal to 1, IC is equal to I. Right? Now what we have been given in the question is that the hydraulic gradient, that is the existing hydraulic gradient, is less than the critical hydraulic gradient. So that means I is lesser than IC. So this falls under the category of first condition where the factor of safety is greater than 1. Alright. Hence the the entire it falls under the safety condition. So none of this sort will occur. So hence none of the options mentioned above. Alright. Now if it is less than I, that is if IC is less than I, then this quicksand condition and piping action might start to uh, would have been occurred. And if it is equal to 1, it will, that is the case where it will trigger the action. Any doubts? Fine. So let us move to the next question. So what will be the discharge per unit length if flow lines and number of drops are 12 and 10 respectively? Assume hydraulic conductivity to be 1.5 into 10 power minus 4 and total head, that is the head difference, to be 5 meters. You can try this problem. Meanwhile, I will be back in a minute. So some emergency is there, so I will be back in. So we will solve this question now. Have you tried this question or did you get any answers? Okay, we'll solve this. So what we have been given is first is the number of flow lines. That is number of flow lines is 12. Number of drops is 10. K is 1.5 into 10 power minus 4 centimeter per second, and delta H is 5 meters. Alright. You can convert this to meter per second also. Then in this case it will come as 1.5 into 10 power minus 6 meters per second. Alright. Now we have to calculate the discharge. Right. Now we have to calculate the discharge, which is given by discharge per unit length, obviously, because this will be infinite in one direction. So the breadth will be assumed as 1 meter. So Q will be K delta H into NF by ND. All right. Now we have been given number of flow lines. So, but NF is defined as number of flow channels. So, if there are n flow lines, there will be n minus 1 flow channels. Right? So hence NF will be, so Q will be equal to K is 1.5 into 10 power minus 6 into 5 meters into NF will be 11, number of drops will be 10. So you should be very careful in while understanding the question, because the number of flow lines, NF represents the number of flow channels and not the number of flow lines. So if flow lines are given, it has to be, if n flow lines are there, then it will be n minus 1 flow channels. So hence it should be modified accordingly. So please take care of this intricacies when you encounter such problems. Alright, now if you calculate it, this can be 2, this can be 5.5. You can just 1.5 into 5.5. So you will get the value as 8.25 into 10 power minus 6 meter cube per second. Alright. Any doubts? Yeah. So coming to the next question, if you have any doubts, you can switch on your mic, because I will be in my press PPT, so that I will not be able to see your chat box. So if you have any doubts, you can interrupt at any time and you can switch on your mic and and speak out your doubts or questions or queries. Or if you want to add some points, you are very most welcome, because this will be in public forum. So large spectrum of people can get benefited from uh, your inputs also. So it is a two-way channel. So I encourage the learners uh, to actively participate and uh, get their doubts clarified. So then, coming to the next question, the flow net for an earthen dam with 30-meter water depth consists of 25 potential drops, that is equipotential drops, and 5 flow channels. The discharge per meter length of the dam is 0.00018 meter cube per second. Then what is the coefficient of permeability of the dam material? Now what they have given is, they have provided us with head, which is 30 meters. This, so ND potential drop is 25, flow channel is 5, Q is 0. What is, or we can write it as 18 into 10 power minus 3 meter cube per second. Alright. Now we need to calculate what is the permeability. So same equation, Q is KH NF by ND. So K will be equal to QND by HNF. That will come to 18 into 10 power minus 3. ND is 25, H is 30, and NF is 5. Now this will be 5. This will cancel as 6. And this will cancel as 3. So K will be 3 into 10 power minus 3 meter per second. Any doubts? Fine. Now then let us move to the next question. So what is the effective permeability, that is some in some units of an anisotropic soil having permeability in one direction as 4 into 10 power minus 4 and in another direction as 9 into 10 power minus 4 centimeter per second. All right. So it is an anisotropic condition. So K equivalent or K effective will be equal to root over Kx into Ky. All right. So Kx is 4 into 10 power minus 4 into 9 into 10 power minus 4. So which will give 10 power minus 4 can be taken outside and it is 36. It will be 6 into 10 power 4, 10 power minus 4 centimeter per second. K effective. I hope the similar kind of problem we have solved in the previous week also. So you should not be facing any issues in this. So now coming to the next question. The flow line makes angle A1 and A2 with the normal to the interface of the soils having permeability K1 and K2 before and after deflection. So select the appropriate relationship according to the law of deflection. So now we have an interface between two soil layers. This is soil layer 1 and this is soil layer 2 and this has a permeability of K1 and this has a permeability of K2. Alright. Now the flow line, that is the flow of water is coming at some direction. This is the normal, sorry. So this is the interface. So let this be the normal line, which is at 90 degrees. Right. Now a flow line is coming like this. And since it is entering into another media having different permeability, so it will deflect in some manner. Alright. Now what they are saying, this with the normal to the interface, that is this angle is A1 and this angle is A2. Alright. Now this will be related, this is similar to Snell's law which we have studied in our higher secondary physics. So it is similar to the incident line and refracted line having a different uh, uh, refractive indices, right? So here, say in a similar way, K1 and K2, K1 by K2 is related as sine A1 by, sorry, tan A1 by tan A2. It is similar to Snell's law of refraction. Alright. So the option will be option C. Any doubts? Okay. Then we'll move to the next question. In a flow net, the length of flow line in the last square is 2 meters. The total head loss is 18 meter and the number of potential drop is 12. The value of exit gradient is. So what they have given is L exit is 2 meters and the total head loss is 18 meters and number of potential drop ND is 12. They are asking us to compute I exit. How we will calculate I exit is delta small h, which is the head loss for the particular flow net. Not flow net, it is a particular flow grid divided by the length of the exit flow channel. Right. So in order to compute this delta H, so let us consider, so there is 12 drops. So the total head loss is 18. So now that at each potential drop, that is each equipotential drop, the entire 18 meters has to be divided equally among the 12 equipotential drop. So at each equipotential drop, the head loss would be how much? Delta H by ND, which is 18 by 12, which amounts to 1.5. And L exit is 2. Now the value of exit gradient will be 1.5 by 2. Both are meters. So this will get cancelled out. So this will be how much? 15 by 20 is 3 by 4, which is 0.75 I exit. Any doubts? Okay. Fine. Let us move to the next question. If the equipotential function for a flow is given by 5 is equal to 2x square y square plus 3, then what would be the component of flow velocity in x direction at point with coordinates 2, 3? So we have been given the potential equipotential function, which is 2x square y square plus 3. Now we need to compute the component of flow velocity in x direction. So now we know this that dou phi by dou x partial differentiation of this equipotential function with uh, x gives us velocity in x, and dou phi by dou y gives velocity at y. Alright, now we need to partially differentiate this function with respect to x. So that will yield us dou phi by dou x is equal to 4x y square. So constant differentiation will be 0. So now you can substitute this is equal to Vx. Alright. Now you can substitute this coordinate in this equation to get your velocity component or along x-axis. So Vx will be 4 into 2 into 9, which is 72 units. Since unit has not been specified, we'll just write as 72 units. Alright. Now if we have to compute Vy, so let us extend this question. So if we have to compute Vy, so dou phi by dou y, which gives us 4x square y plus 0. In this regard, Vy will be at the same coordinate will be 4 into 4 into 3. So 16 threes are 48 units. Alright. This is for equipotential function. Now let us extend this question by treating this as stream function. Stream function is psi. Psi is equal to 2x square y square plus 3. Now with this as stream function, now we can calculate the velocity component along x and y. So the identity will be dou psi by dou x will give you Vx, Vy, sorry, Vy, and dou psi by dou y will give you minus Vx. Alright. Now let me erase this part. Sorry. Now coming to this part, now we will differentiate this with x. So now we know the differentiation dou psi by dou x will give us the same function, which is 4xy square. That will be Vy in this case. So which will give at this coordinate we will get 72 units as Vy. And for Vx we will get dou psi by dou y is equal to 4x square y, which is equal to 48 units is minus Vx. So Vx will be minus 48 units in the other direction. So this is just to understand how From the Laplace equations, these stream functions and potential functions are used to derive the velocity components. All right. Any doubts? If you have any doubts, you can get it clarified. Fine. So coming to the next question, calculate the seepage force acting on a road of width 7 meters, which is under the exit gradient of 2. So seepage force of width 7 meters, which is under exit gradient of 2. So we know seepage force per unit volume is I into gamma W. So seepage, sorry, let it be small fs. Seepage force per unit volume. So for the complete volume, since this road is independent, that is, the other directions are infinite. So what we do is we assume other dimensions as 1. So I into gamma W into L into B into H. So let length be 7, B and H be 1 meters. Right? So let gamma W be 10 kilonewton per meter cube. Now seepage force and this at this condition will be I is 2 into 10 into 7 into 1. So that will be 27 or 140 kilonewton. Any doubts? Fine. Now coming to the next question. So the Laplace equation for water flow in porous media is given by dou square h by dou x square plus dou square h by dou y square plus dou square h by dou z square is equal to 0. And head does not vary in y and x direction. The boundary conditions that are given are x is equal to 0, h is equal to 5 meters, and dh by dx is equal to -1. What is the value of x at h, value of h at x equal to 2? Right. Now, coming to the this is the Laplace equation we know, and the major condition what they have specified is that regarding this question is that the head does not vary in y and z direction. So that means dou h by dou y is 0. Dou h by dou z is 0. And hence this will be 0 and this will be 0. So hence we have the only equation dou square h by dou x square is equal to 0. Alright. Now we have to integrate it. Right. So first time integration will give us dou h by dou x. In this case, it will be dh by dx only, since there is no other variable, which will give us c1. All right. And finally, h will be c1x second time integration plus C2. Alright. Now at x equal to 0, first boundary condition is at x equal to 0, h is 5 meters. So this will be 0, C2 will be 5, right? And dh by dx is minus 1, hence that is equal to C1, which is minus 1. Alright. So now the equation will be h is equal to C1 is minus x plus 5. So now the head at x equal to 2 will be 3 meters. Alright. Any doubts? Fine. Now moving to the next question. A sand deposit 12-meter thick overlies a impervious soil mass. So a sand deposit 12 meters overlies an impervious soil mass. The vertical sheet pile penetrates 5 meters into the soil deposit. The water level on an upstream and downstream side is 3 meters and 1 meter above the ground surface respectively. The horizontal and vertical permeability for the sand deposit are 4 meters per day and 1 meter per day respectively. A flow net construction reveals that there are 12 flow channels and 24 equipotential drops. Determine the seepage flow per day. Calculate the exit gradient if the average length of the last element is 0.9 meters. So for that we have to first depict the question in a diagram. So what we have been given is that this is the ground level. Sorry. So this is the ground level. Alright. Now we have a sheet pile. Sorry. So this is ground level. We have sheet pile inserted into the right. So the upstream length is height. Depth of water is 3 meters and downstream depth of water is 1 meter above the ground surface. Alright. Now this is extending up to 5 meters. So this is, as far as this is concerned, it is immaterial. Now what other things they have given is, so this layer extends up to 12 meters. Right. Now the major thing they have given is there is an anisotropy associated with the permeability. So the permeability coefficient at along x and y directions are different. So that is known as anisotropic behavior. So in this condition, we have horizontal permeability as 4 meter per day and vertical permeability as 1 meter per day. Hope I'm correct then. Now, other thing we have is NF is 12 and ND is 24. Number of flow channels is 12 and number of equipotential drops are 24. Now, what we have to find is, we have to find what is the discharge that is taking place and I exit. Alright, for that we need to first estimate the head loss. So head loss capital H is equal to upstream height at the upstream end minus height at the downstream end, which is 2 meters. Alright, now as per the Darcy's law extended for two-dimensional flow, K effective into head loss into NF by ND. Alright, so the K effective has to be calculated since it is an anisotropic flow. So which is equal to Kx into Ky, which gives us 4 into 1, which is 4. Root gives us 2 meter per day. Square root gives us 2 meter per day. So now calculating Q will be 2 meter per day. H is 2 meters and NF is 12 and ND is 24. So this gives us 1 by 2. This gives us 2 meter cube per day. So this is the discharge that takes place. Now coming to the exit gradient. So I exit, which is determined as IE, which is equal to delta small h, which is the head drop within one flow grid by the length of the channel, length of the flow channel. So length of the flow channel is given to us as average length, so that can be taken as the length of the exit flow also. And for computing delta H, we need to calculate capital H divided by ND. So that will give us H is 2 meters, ND is 24 into 1 by 0.9. So this will be 1 by 12. So if you multiply it, I exit will be 0.0925. Right? Any doubts? Any doubts? Fine. So coming to the last part of this last question here. So this is one of the practical applications where so in the previous question I have discussed the uh, usage of flow nets, right? So how to determine the pressure head or hydrostatic pressure along the flow path. So this question is one of the perfect examples to understand the concepts. So here the figure below shows a sheet pile driven into a soil layer having a hydraulic conductivity of 4 into 10 power minus 6 meter per second. So calculate the discharge on the downstream end. Tabulate the water pressure acting on the pile along the points from A to I. So if you zoom the picture a bit, you can see several points listed from A all the way to I. All right. So now we have to understand some of the given information by listing them down. So first is K, which is 4 into 10 power minus 6 meter per second. All right. So next is, so first is a discharge has to be calculated. So now for that we need to calculate what is head difference. Head difference is 30 minus 22.5, which gives us 7.5. So next is NF, number of flow channels will be 1, 2, 1, 3. And number of equipotential drop is 1, 1, 2, 3, 4, 5, 6, 7, and 8. This is 8. Alright. Now we have to calculate the discharge. Q is equal to KH NF by ND. So which is K is 4 into 10 power minus 6. So H is 7.5 into NF is 3 and ND is 8. And this will be 1, this will be 2, and this will be 1.5. So if you multiply them, 1.5 into 7.5, which will give us 11.25 into 10 power minus 6 meter per second. So this part of the question has been solved. Now the coming to the second part of this, so this will be fairly straightforward. I hope you understand how we have created this drop and calculation of NF and ND. Now coming to the water pressure at several points. So for that we need to tabulate it. So let us create a table here. So this is point. Right. Now let us we calculate the elevation head. So here in this case, water pressure is nothing but pressure head. All right. So for that, we need to calculate the pressure head at each and every point during the flow. Earlier, it was no single direction flow. So hence, it has been easier for us. Now it is two-dimensional flow. For that, we need to use. We can see how flow net is used here. So this is elevation head, and this is total head, and this is pressure head, and this is water pressure. Water pressure is defined as pressure head into gamma W. So gamma W can be taken as 10 kilonewton per meter cube. Alright. So this is the table which we are going to fill. Right. Now let us list down the point A, B, C, D, E, F, G, H, and I. Right. Now elevation head. So this can be treated as the reference point. So and hence there in the question has also been there in the question also it has been depicted. So A is at a elevation head for A is 30. B is 20. C is 16. D is 10. E is 5. F is again 10. G is again 16. H is again 20. And I is at 22.5. Understood? Any doubts? We are just calculating the elevation head. Alright. Now coming to the total head. So how to determine the total head? So here now we have to understand what is actually happening. So here at point A, the elevation head is 30 and the pressure, if we keep the uh, piezometer here, it will give 0. It is at the atmospheric condition. So pressure head at A is 0 and the total head is 30. Understood? So this is everything is in meters. This will be in kilonewton per meter square or kilopascal. All right. So similarly at B, so if you keep the piezometer here, it will again rise to this point. So that will be, so elevation it is 20 and if you keep the piezometer here, sorry. So the water will rise up to here in the piezometer. So hence the pressure head will be 10 and the total head will be 30. So which states that there is no flow occurring from here to here within the column. Alright. Now the total head, now imagine the total head here is 30 and similarly here also the total head will be 22.5. Let us come, it will not be 22.5, let us come back further. So let us be frank, let us be this. So now at point H, correct? Now at point H and at least at point I, so it is at atmospheric condition. So point I, it will be 0 and it will be 22.5. All right. Now the head difference between point A and point I is 22.5. That is head difference is nothing but the water is losing its energy to flow. That means across this path, entire path, the total head loss that has been occurred is 7.5 meters. Right? Now we have 8 flow that is equipotential drops. That means this entire 7.5 meters is divided into 8 equal parts such that uh, when the water crosses all these 8 equipotential drop, the head loss will be 7.5 meters. So what will be the head loss for each potential drop? So that will be delta H. That will come to 7.5 divided by 8. Okay. So if we calculate this 0.75, sorry, 7.5 divided by 8. So that will be 0.93. All right. So now it is fairly easy. Now we can directly calculate the total head here. So this entire thing gives us the total head. Now it is at B, it is 30. Once it reaches C, the number of potential drop is 1, and hence it will be 30 minus 0.93, right? That will give us 29.07. So once it reaches D, it is 29.07 minus 0.93, which gives us 29.07 minus 0.93, which gives us 28.14. So in between that we have another drop here. So here at point E we have two drops. Hence 28.14 minus 2 into 0.93. Right? So 28.14 minus 2 into 0.93. So that will give us 26.28. Alright. Now coming to the fifth point, or F. Again, the number of flow equipotential drop is 2. So again it will be 26.28 minus 2 into 0.93 minus 2 into 0.93. So that will give us 24.42. So again coming to point G, it is one equipotential drop. So for that it will again come to 24.42 minus 0.93, which comes here 24.42 minus 0.93, which comes to 23.49. And again this will come back to minus 0.93. It will come approximately, again it will come back to 22.5 here. Alright, some minimal, this is due to decimal issues. So it will come to 22.5 at H. And H to I, there is no change in flow. There is no flow occurring. So now what we can do is, we have filled all the total head and elevation head. Now we can get the pressure head, which is total head minus elevation head. So now you can separate each column. 29.07 minus 16. So that will give us 13.07. And here 28.14, it will be 18.14. And here 26.28, it will come back again to 21.28. Again now it comes to 14.42. Now it comes to 7.49. And now it comes to 2.5. And this comes to 0. Alright, now you can see the pressure rate up to when it reaches E, it is increasing and then it starts to decrease. Alright, so now in order to compute water pressure, you can just multiply this, you can take it as 10 kilonewton per meter cube. You can just multiply by 10. 0, 100, 130.7, 181.4, 212.8, 144.2, 74.9, 25 and 0. So this is how pressure heads are calculated for this type of problems where flow is occurring. So you cannot just keep your piezometer here and it will raise to here. In that case, every pressure head will not. In that case, both C and G should have so that part it should not be done like that. All right. So the flow occurs here, and during that flow, we will just calculate the pressure heads at these points. Okay. Any doubts? If you have any doubts, please. Okay. So with this, we will stop the session for today. So thank you for attending. And these sessions, hope it was useful. Now these sessions uh, will be conducted on Saturdays 5 to 7 p.m. And I encourage the learners to uh, participate actively and get your concepts clarified and get proficient with the concepts. So I'll be thank you all. We'll meet next week at the same time. Okay. So I am closing this meeting. Thank you.